Hi everyone, my name is Mihir Joshi and I am excited to share with you all my AMME undergraduate thesis project, Scrap, a climbing robot for planetary exploration. Let's start with a quick look at why a climbing robot would be useful for planetary exploration. Exploration on Mars, for example, has mostly involved the use of ground exploration vehicles such as planetary rovers. To gain a deeper understanding of the geology of rocky planets like Mars through stratigraphy, we seek to benefit from exploring natural cliff faces by climbing them. Uncovering the geological history of Mars and its composition in this way can reveal information that was previously unattainable by ground-based rovers. This exposes the motivation to develop a climbing robot that can traverse on rough, inclined surfaces for scientific gain. So the research question of this thesis was, how can a rough surface be scaled or adhered to and climbed with a climbing robot? So how can we climb and scale a rough, inclined natural surface? The concept of microspines can be exploited to generate adhesion forces to the surface. Microspines are small hooks that can engage surface asperities that exist on rough surfaces, and it's basically how insects can climb on walls. Surface asperities we can exploit are called effective asperities, and the number available for use is dependent on the size of our microspine tip. The climbing of a rough surface is a probabilistic problem, where the distribution of effective asperities on a particular surface area approaches a Gaussian normal distribution. The rougher the surface is, the more effective asperities are present, and therefore the more likelihood there is of a successful attachment. Let's take a look at the forces in play when climbing. Drawing inspiration from animals that climb, a climbing robot should be designed with a tail. Including a tail reduces the load that is placed on each microspine, preloading forces normal to the climbing surface. This means that less adhesion forces are required for adhering to the surface, making the climbing process less demanding for the spines. To allow for steering control, a differential drive system can be designed for the robot, enabling steering capability with just two speed-controllable wheels driven by high-torque 12-volt motors. So now that you have an idea of how climbing actually works, allow me to take you on my journey to develop and test the robot. First, I needed to make sure that climbing rough surfaces was possible with some basic materials that were available. I built my first climbing robot prototype with PVC, door stops for wheels, and a 9-volt battery for the motors, and tested it on a brick wall. After validating the concept, it was a matter of designing a new and improved robot, which was designed in SolidWorks and then 3D printed. The robot was assembled using fasteners and threaded designs. So the robot has a 6 degree of freedom inertial measurement unit, or IMU, which is used to determine the surface inclination on which the robot is climbing across both roll and pitch angles. The robot is powered with a 11.1 volt LiPo battery, allowing for greater mission lifetime and general climbing performance. The robot is controlled with the ESP32 microcontroller and communicates over Bluetooth Low Energy with the ground station. The ground station involves an easy-to-use user interface that enables remote control over the robot with the use of a PlayStation 3 controller connected to the computer over USB. So let's take a look at how the robot performs. To start us off, here is the robot's on-ground steering ability. With the use of the joystick, the user has the option of turning the robot left or turning right. The robot can also perform a horizontal to vertical transition as shown here from a coarse, paved gravel surface to a vertical brick wall. The robot was controlled to approach the brick wall and adhere to it. Now for actual climbing, you may notice the white strings that are tethered to the robot. They are simply a lifeline to protect it from potential falls. Here we see Scrap climbing a vertical brick wall where slips can be recovered from thanks to the tail, high torque motors, and the placement of fishing hooks on both wheels. Here we see Scrap climb a roughly 50 degree incline toward an overhang. The robot attempts to overcome it, but does not engage effective asperities to do so. And finally, for a near vertical rocky inclined surface, Scrap can grasp onto the available asperities on the surface and climb a 1.4 meter tall rock with only slight slips when the surface profile was a bit smoother. So there you have it, the climbing robot Scrap showing its ability to ascend upwards. Future work would see a design modification making way for a method of reliably descending from a height it reaches, amongst room for autonomous operation. In this thesis, a climbing robot was developed to traverse on near horizontal surfaces, make transitions to the vertical, climb vertical brick walls, climb rocky inclined surfaces, and finally climb near vertical rocky surfaces to prove its applicability for planetary exploration. After the literal blood, sweat, and tears that went into undertaking this project, I am glad to announce the robot is still in one piece, and if that's a measure of success in engineering, I will gladly take it. Thank you all for listening, and thanks for your time.